Thank you very much for a nice introduction. Yes, we flew from Melbourne. Max flew from Melbourne via Egypt. So, hello, I'm Mark Feldman from Afterpay. I would like to talk to you today about real-time payments with Temporal. We'd be happy to answer your questions at the end of the talk. When we talk about temporal workflows, we imagine workflows that run for hours, days, or even months. Our case is different. Our workflows run in seconds because they process real-time payments. First, a couple of words about Afterpay. Afterpay is a fintech company, part of Block, originally based in Melbourne, Australia, and now everywhere. We provide financial services such as pay in 4 installments to our customers in Australia, New Zealand, North America, and Europe. Our customers use Afterpay to make purchases and pay for them later. Afterpay pays the merchant for a purchase, and the consumer pays us back in 4 equal installments without interest. Customers love to use Afterpay to manage their budgets, but there is a limit to how much one can spend with Afterpay at any given time. To free up their spending limits, customers don't have to wait for their automatic deductions to go through. They can choose to pay installments manually at any time. We work in a team that builds a system that processes Afterpay payments. Lots and lots of payments. In fact, we process millions of payments every day. But to better understand the payment specifics, let's talk about different types of payments and how we process them. There are 2 major types of payments. Customer present, or we call them online. When a customer makes a payment in store or online using a web portal or a mobile app. And customer not present or offline, when a payment is deducted automatically by Afterpay on behalf of a customer. These payment types differ in their latency limits and requirements, with customer present payments having much stricter timeouts. So how do we process a payment? Well, we take a series of steps that involve multiple systems, both internal and external. First, we load data from other systems to validate the consumer to make sure that they are active and can make a payment. Then we validate a card or other payment method to make sure it can be used as a payment, to make a payment. We also validate the payment details, such as the amount, to make sure it's correct and that the installment has not already been paid. Then we ask a payment gateway to transfer funds. We save payment details to our database. We let other services know about this payment right now. And we also publish Kafka messages for other systems who want to know about this payment later. We notify a consumer via email. And then finally, we return the result back to the consumer if present. All of that within a short period of time, about 2 to 4 seconds. It is one giant distributed transaction. And a lot of things can go wrong in this distributed transaction. And when they do, we want to roll back across all systems. Orchestrating services and recovering from failure is an increasingly complex task. For example, we may need to reverse a payment if we fail to update our database. Is it the same as refund? No. To refund a payment means to return the money from merchant back to consumer. Afterpay sits in the middle between merchant and consumer and facilitates their refund. But with reverse, to reverse a payment, we ask the payment gateway to cancel their funds transfer request as if it never happened. Before using Temporal, failures of these distributed transactions sometimes resulted in orphaned or duplicate payments, occasional data loss, and required manual cleanups and compensations. Hence our motivation with bringing Temporal into the picture. We need eventual consistency across all parties, flexible sucker compensations, and firm resilience to failure. Now I want to explain a few things about what we consider short-running and long-running workflows, because a lot of different contexts use the same terms differently. What is the difference between short and long-running workflows when it comes to payments? Well, essentially, it's different SLAs, length of timeouts, and the number of retries. Also, for US customers, we have special ACH workflows. We call them extra long-running workflows. US customers can pay with ACH bank accounts. ACH is the automated clearance house, and it works a bit like a direct debit in Australia. A typical ACH payment requires 5 business days to clear. So in general, it's about 7 days, or on holidays during Christmas period, it may take up to 15 days altogether. It means that some of our workflows wait for several days for ACH confirmation to finalize a payment, even when a payment is made online. Now I'd like Maxim to talk about some of the technical issues that we faced in payments processing.
Thank you. Hi everyone. Let's talk about reliability and performance of payment processing with temporal workflows. Running low latency workflows is a fine art. Temporal brings a lot of capabilities, but also has a certain overhead. It requires very careful consideration of timeouts, fine-tuning of retry policies, and compensation steps. And there is also a balance between reliability and performance, because having longer timeouts and many retries, it definitely improves reliability. But in this case, performance will suffer and our SLAs might be broken as a result. We've been running temporal workflows in production for more than 2 years and processed in total more than 1 billion payments over this period. And I would like to share a few lessons about reliability and performance that we learned while running temporal workflows for low latency payment processing applications. Sorry. One lesson we learned was about task queues. Here is the problem. We used a single task queue for all our activities, but for online payments, our activities have short timeouts, limited retries, and they must execute or fail fast. On the other hand, for offline payments, activities have longer timeouts and many more retries, so they are more resilient to failure. So now imagine when a downstream system begins to fail or just goes offline. Those activities with more retries and longer timeouts start to occupy more and more room in the task queue and activity execution pool. And eventually, all available workers are busy retrying long-running tasks. And there is almost no room left to execute our short-running activities. The result, online payments start to time out and fail SLAs. The solution to this problem is very simple but effective. We split the activity task queue into 2, for short-running and long-running activities. And we define dedicated workers to process short-running activities independently from others. As the result, we allow online payments to maintain SLAs, and at the same time, we let the long-running task queue to deal with high volume, longer recovery times, and more generous retry policies. On this slide, here is an example of how we configure our activities in Kotlin. So we created a custom activity options annotation, and it can specify many options, such as different types of activity timeouts, start to close, and so on. Assign a specific task queue for short running or long running. Define the need for a distributed log. I will talk about this a bit more later. Also, we use the standard temporal method retry annotation to configure activity retry policy. All of that helps the developer to reason about performance and behavior of activity executions. Now, let's have a look at another lesson about reliability versus performance. How to optimize a workflow to minimize response time for low latency. For example, we have a workflow that processes an online payment, and it must return the result back to the waiting user. This workflow takes a number of steps to process a payment. Some of them can spend a lot of time in a downstream system, which we do not control. As we have strict SLAs, but we also would like to maximize our chances of success, even when downstream system fails. How do we achieve that? So we split our workflow into two parts. Let's call them critical and finalization. First, critical workflow. It executes all important tasks and fail fast if necessary. Then it asynchronously starts a child workflow, we call the finalization workflow, and then immediately returns the result back to the user. When we start a finalization workflow, we provide enough context to execute remaining tasks. Run compensation or maybe both. This is important. When running a critical workflow, we do not run compensation activities in it. Why? First, it takes time to compensate, but we need to minimize the overall response time. Second, the same thing that caused an error in the main workflow may also cause a compensation failure and may require more time to succeed. For example, when we have downstream service degradation. So instead, we push all finalization or all compensation actions to the finalization workflow. And then we execute them durably in that workflow, given enough time to succeed. And to summarize, we separate all important steps that are required to synchronously produce the result from the rest, thus minimizing the response time from the user's perspective. Well, but what if it's not enough? Temporal does add some overhead, in our case at least 200 milliseconds or even more, to the overall processing time. In some use cases, it's too much of overhead, and the question is it possible to reduce the processing time even more to get a predictable low latency? The answer is yes. If the critical part must fail fast, there is a way to shorten it even further. Well, it might not work in some cases. The critical path must be simple enough to allow for this optimization. And to be honest, we don't use this a lot, but in some use cases, that can be very useful. So how do we do that? First, we run the critical logic directly in the application server context, so we do not use temporal workflows at all for this part. Instead, we start the finalization workflow asynchronously at the very beginning of the critical part execution. Then we update the finalization workflow about execution progress. So we use workflow signals to send necessary data required for finalization or compensation. And it's very important. Always start a timer at the beginning of finalization workflow, so it triggers compensation if no signals received. It can happen when the application server crashes, for example. What are the benefits of this approach? First, temporal related overhead is almost completely removed from the critical part, so it runs fast. And finalization workflow runs all activities asynchronously and durably, using appropriate timeouts and retry policies. As the result, we reduce the overall latency of our process and make the critical part execution more predictable. On the downside, critical part loses all temporal benefits like reliable or durable execution, but we still achieve eventual consistency and resilience to failure because we have finalization workflow. Now let's talk about workflow and activity timeouts. We will look at two slightly different use cases. First, when the whole workflow execution is limited by some factor. In our case, it's by distributed locks. And second, when we need to control the timing of what we run inside an activity. Let's talk about timeouts imposed by distributed locks first. What is a distributed lock in our case? When we process a payment, we mutate the consumer state. And mutating state requires a distributed lock to prevent concurrent modification by multiple systems. We cannot mutate customer data without holding a lock, or after the lock expires. Distributed lock has limited lease period, therefore it limits the workflow and activities execution time. And once acquired, the lock lease cannot be extended. Finally, within the lock, a workflow must complete before the lock expires or terminate with failure. So how do we deal with distributed locks in workflows? We created a custom activity interceptor to keep track of time left in the lock. And we allow an activity to start only if the lock has not expired yet, and activity has enough time to complete within the lock lease period, based on activity options and timeouts. Otherwise, we throw a timeout exception, which causes the workflow to terminate with failure and trigger all necessary compensation. Now let's go down to the activity execution level. We encountered an interesting issue with activity timeouts and SQL queries, especially with those queries that insert new records. Here's the problem. Sometimes a database query can take a very long time to execute, for example, due to internal database logs or slow database performance in general. And when a query gets stuck, it may force the activity to run past its start to close timeout. When that happens, Temporal server may decide to retry the activity based on its options before the query has completed. The next activity execution attempt runs into exactly the same problem and gets stuck too. When Temporal server exhausts all the retries, activity completes with failure, causing the workflow to terminate. But despite all that, the query may actually complete successfully and even create new database record on each execution attempt. And when we have insert queries, it leads to duplicate records and general data inconsistency. The solution is actually quite similar to the previous one. We use a database query interceptor to keep track of time left in activity start to close timeout. And then we dynamically set the query timeout to fire before the activity times out itself. Also, if a database transaction runs over the start to close activity timeout, for whatever reason, it's also terminated with an exception. When terminated, database transaction rolls back and allows the activity to retry safely, so we don't have any data consistency issues anymore. It's quite important that this type of timing control is relevant not only for SQL queries, but for actually all types of external requests, especially mutating data. It can be REST or gRPC calls. All right, that's all I wanted to share with you today about reliability and performance for payment processing. Now Mark will continue with another important topic, high availability.
Thank you. I'd like to share a couple of features that helped us with high availability. These features do not guarantee high availability, but they are very helpful in the long run. First one is Protuff. Temporal uses Protuff in the gRPC API, and it works well for them. We decided to use Protuff in all our workflow activity and method parameters. That slide that you saw just a few minutes earlier with an example of activity interface. all those parameters there are actually our Protuff definitions. It helps with high availability by maintaining backward compatibility of parameters. It helps maintain the compatible workflow code. It enforces version control on parameters, and it also reduces payload size because it's binary. The last but not least, I'd like to share our disaster recovery solution for temporal workflows. This was all developed a year, maybe 2 years ago, before global namespace was out. And this solution served us well in the last few years. We never actually had to use it for disaster recovery, but it helped us maintain, migrate of temporal clusters internally and to the cloud. The solution serves two purposes. One, to provide an acceptable mechanism for DR of self-hosted temporal cluster to spin up a new cluster in a secondary location, and also to assist with moving to another cluster. Sometimes we need to move to another cluster because a self-hosted cluster cannot perform an in-place upgrade when you're stuck on the old version and it's no longer compatible with the new one. Or if you want to relocate the cluster to a new, different network location. But the best example would be if you want to move from self-hosted to temporal cloud. The solution we call MultiCluster Operation. We can configure our system to work with multiple temporal clusters at the same time. One cluster is always active, all others are passive. Active means the cluster can start new workflows and run existing ones, and passive means the cluster can run existing workflows but cannot start new ones. All clusters are supported by identical sets of temporal workers running the same version of the workflow. We also use an in-flight registry database table to keep track of long-running workflows, recording their workflow ID and cluster name, among other things. When a workflow starts, it registers itself in that table, and when it finishes, it removes itself from the table. We use this registry to locate the running workflows so we can send signals to it. Signals are usually sent by Kafka consumers. We can switch from passive to active at any time. When all workflows are done in a passive cluster, we can unlink it and shut down the workers. Disaster recovery is slightly different from planned migration. DR event usually means the loss of an active cluster. In this case, all short-running workflows will fail or time out, and we will not fail over them. But all long-running workflows must fail over to a new location. If an active cluster is lost, we provision and switch to a new active cluster in a failover location, which will be empty from the start. We activate it and operate it as normal. Then we start to recreate the long-running workflows using a special recovery workflow. It uses our in-flight registry and a database state to recover all those workflows. The only downside to this is that every long-running workflow must have such a mechanism available. When we're ready to fail back, we add a new passive cluster in our primary location and activate it. When all workflows are completed in a secondary location, we just shut it down. Let's recap what we learned today about low latency workflows. A few ways to deal with reliability and performance. Split task queues split workflows into critical and finalization parts, and exercise time and control over activity execution, SQL queries, and other network requests. To maintain high availability, use Protuff for method parameters in workflows and activities, and employ multi-cluster setup for DR and migrations. Thank you for your attention. You can contact us on email or Temporal Slack channels. And thank you for your time.